right, great morning. Welcome to day one of e-learning. This is going to be an example of a chi-square test for independence. We're going to be going through our notes on chapter 11 notes, page 9, and I would recommend you, if you can, watch this video on a different device than your iPad. That way you can take notes on your iPad and watch the video simultaneously. So the first thing that you need to know is that when we are doing a chi-square test for independence, it's pretty much the same procedure as a chi-square test of goodness of fit, but it's fundamentally different. And you can already see that based on, if you look at the notes, that the data is set up differently. So let's read through the problem. The article motion sickness in public road transport, the effective driver, route, and vehicle reported that seat position within a bus may have some effect on whether one experiences motion sickness. The following table classifies each person in a random sample of bus riders by location of his or her seat and whether nausea was reported. Based on these data, can you conclude there is an association between seat location and nausea? Test the relevant hypotheses using alpha equals 0.05. So, when you see this problem, and you see it written, especially in that last sentence, can you conclude there is an association between seat location and nausea? That's the clue that this is a chi-square test of independence or association. Now, it's called the test of independence or association. Those are synonymous. Sometimes you'll see it written with this phrase, independence. Sometimes you'll see it written in this phrase, association, but it means the same thing. Also notice how the data is fundamentally different than a goodness of fit test. When we did a goodness of fit test, we have one row of data or one column of data. And we're testing how well that data fits a known or hypothesized distribution. In this case, we have a two-way table. And if you recall from first quarter, a two-way table was used when you have two categorical variables. That's what we have here. We have nausea, which has two categories, nausea or no nausea, and we have seat location, another variable, which has three categories. So we have two different variables, and we are testing whether these two variables are associated in any way. Just based on my knowledge of riding on a bus, I would suspect that those people sitting in the rear would be more likely to experience nausea than those that are sitting in the front or the middle. But that's what the test is for. We're testing to see if there is actually an association between location and nausea. So, check out our hypotheses. The null hypothesis, recall that null means no change or no difference, or in this case, no association. No association is the same thing as independence. Okay, if there is no association, the two variables are in fact independent of each other. So we are assuming with the null hypothesis that there is no association between seat location and nausea. We're going to assume that they're independent, and we're going to look for statistically significant evidence of the contrary. We're going to look for statistically significant evidence that there is an association between seat location and nausea. In other words, we're going to test if they are dependent. You can see I've already calculated the marginal totals. Remember the marginal distributions? These red numbers, those are the marginal totals, the marginal distributions. All the numbers within the table itself are the conditional values. So based on our marginal totals, we have a total of 3,256 total bus riders that were surveyed, and a total of 12.8% of them experienced nausea. So if there truly is no association, if we assume the null hypothesis is true, then that means we expect 12.8% of bus riders sitting in each region will experience nausea. So we would expect 12.8% of these 928 front riders would experience nausea, and 12.8% of the 1,329 bus riders in the middle to experience nausea, and 12.8% of the 999 bus riders in the rear to experience nausea. Now I haven't calculated the conditional probabilities in here, but I would guess they're not equal to 12.8%. Okay, we're really going to test to see if there is statistically significant evidence that this sample was unlikely to have occurred by chance alone. Let's talk about our assumptions. We have the same basic three assumptions that we've had throughout the other hypothesis procedures that we've done. We still have our random sample assumption. We were told that the sample is a random sample of all bus riders, so that's satisfied. We still have the 10% condition. We still, our sample size was 3256, so I made a statement there are more than 32,560 bus riders in the population. Seems reasonable. And the large counts condition, we still have to assume, just like with the chi-square test for goodness of fit, the condition is that all expected counts are at least 5. Okay? So we have to calculate the expected counts. These are the observed counts that actually were collected in the sample. We have to calculate the expected counts. So with a two-way table, we have a formula to calculate the expected counts, and that's this formula down here. So this is not a formula that's on your formula sheet, but it's something that you're expected to know. You're expected to know how to calculate the expected counts for any given cell. I've done one example for us. So this first cell, here are the expected counts. I already calculated them all. But the first cell, which is the upper left-hand cell, the front nausea cell, if we were to calculate the expected counts in the front nausea cell, we're going to take the row total times the column total divided by the table total. So for that upper left cell, we would take the row total, 928, whoa, excuse me, that was lunch, 928, times the column total, which is the 417, divided by the table total, the 3256. And that's how we come up with the expected counts for that first cell to be 118.85. Okay. Now you're not going to have to do this for every cell. This is a lot of calculations. Your calculator will do all this for you. Okay, I'm going to show you how to do that. So they go through this in the textbook, in the reading, but I'm going to try to show you on my calculator how to do it. And okay, so get your calculator if you don't have it. Okay. All right, I hope you can see this. So the first thing I'm going to do is when we perform a chi-square test of independence on our calculator, we're going to use matrices. Okay, so the matrix menu, you got to find that on your calculator. For me, it's right here. If you have one of the newer versions, it's going to be along the left-hand edge, I believe. So I'm going to click the matrix menu, and it's going to give me this first screen. And if you have matrices already defined in here, that's fine. It doesn't matter. We're going to select the first matrix A, and we're going to edit it. Okay, so I'm going to scroll to the right. See up here on the, you see that right there. Okay, so we're going to scroll to the right. We're going to click the edit option, and we're going to push enter, and we're going to edit matrix A. Now, matrices are typed in as rows by columns, so that it's kind of hard to see this. 3 by 2 is what I've typed in at the top because there are 3 rows and 2 columns in this matrix. Okay, so this is a 3 by 2 matrix. And you don't have to include the row totals or the column totals in your matrix. So I typed them all in, 58, 870, 166, 1163, etc. Okay. After you type in the observed counts, that's all you need to type in is the observed counts into the matrix. Then you're going to go to the stat menu, and you're going to go over to tests and down to the chi-square test, and you're going to run it. And you're going to get this menu here, and it says observed, expected, calculate. Now that first line where it says observed, that's basically saying where did you put the observed counts? And you're always just going to leave that as matrix A because you're always going to put the observed counts in matrix A. The second row says expected, and that's basically the calculator saying, where do you want me to put the expected counts? So your calculator is going to calculate the expected counts and put them in the matrix that you specify. Now I just always leave it as matrix B, and then it'll just constantly overwrite the existing matrix B. And then you're going to push calculate, and you can see it gives you the test, it gives you the chi-square statistic, it gives you the really small p-value, it gives you degrees of freedom equals 2. But as far as the expected counts go back to your matrix menu and go down to matrix B, and now you're going to notice, maybe this wasn't there before, you'll notice that matrix B is now defined as a 3 by 2 matrix, and more importantly, if you click on it, you can see what all the expected counts are. So what you're going to do is you're going to take those expected counts and you're just going to copy them onto your assumptions. You're going to copy them into a table form, kind of like I did on the board, and that's how you're going to get your expected counts. It's a lot easier than doing it by hand. You can scroll to the right too if you want to see them all. Okay. I know that was kind of hard to see. If you go in the textbook, they show you all those steps in the textbook in the part of the reading. So anyway, as far as the large count condition goes, we needed all of our expected counts to be at least 5. All of our expected counts are very large, so our sample size is sufficiently large to use chi-square procedures. Again, this is not normal. There's nothing normal about a chi-square procedure. We don't use the word normal in our assumption at all. We're just using the sample size is sufficiently large to use chi-square procedures. Okay. So let's go on. I'm going to turn this around. Okay. Make sure you can see this. Looks good. Okay. All right, so back to our chi-square test for independence and association. Here's our observed counts. I just rewrote them on this side. Here's our expected counts. I wrote them back up here. The chi-square statistic is the same formula that we used for the chi-square goodness of fit test. You still have the chi-square components like we did before. It's the sum of all the observed minus expected squared over expected. So you're going to take each of the 6 cells. Again, don't have to worry about the totals, the row totals or the column totals, only the cells themselves, and you're just going to add them all together. So 58 minus 118 squared over 118 plus 87 minus 809 squared over 809 plus, and I'm just going to use a dot dot dot. You have to do that for all 6 cells until you get to the last one. 806 minus 871 squared over 871 gives us our chi-square statistic of 73.789. And again, that's what the calculator spit out when you ran it on your calculator. Most likely you're just going to let your calculator do the work for you. The p-value, you also saw the p-value that your calculator gave was this 9.48 times 10 to the negative 17. Again, you have this skew to right distribution. We're always finding the area to the right of the test statistic. The degrees of freedom. When you saw the calculator gave us 2 degrees of freedom, that was based on a slightly different formula to calculating degrees of freedom for a chi-square test of independence. So the formula for degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So we had a 3 by 2 matrix, 3 rows, 2 columns. So we had 3 minus 1 times 2 minus 1, and that's how we got 2 degrees of freedom. The decision and the conclusion is essentially the same. Due to a small p-value, we reject the null hypothesis, and we do have statistically significant evidence that there is an association between seat location and nausea. Okay. Okay,